very pleased to introduce Dr. DJ Luscher, who's be speaking today about deformation behind shock waves. He's from Los Alamos National Lab, where he's a technical staff member in the theoretical division. He got his PhD in mechanical engineering from Georgia Tech about 10 years ago. His interests are in constitutive theory development for materials in extreme dynamical environments. And DJ actually joined Los Alamos as a graduate student and then went back to school. So he has been with the lab, I believe, almost 20 years now. And he can speak more about his experience at the lab. So with that, very pleased to introduce today's speaker. And I'm going to stop sharing my screen. So DJ, you can share your slides. Okay, and the participants, if please be muted, and you can enter your questions in the chat anytime. Okay, DJ, you can start. You see a blank screen right now. So DJ, you are muted and we see a blank screen.
Okay, thank you.
Okay, we hear you now. But we don't see your screen. Okay, now we see it. All right, great.
Now you see the screen? Okay.
Yeah.
All right, so if somebody types in a comment and I don't notice it and somebody else, maybe Ahmed, maybe you could just give me a heads up.
That's right. So
okay,
people can keep typing, and if needed, we'll stop you, but otherwise we do the Q&A at the end.
Okay, thank you. So I'm DJ Luscher from the Theoretical Division at Los Alamos National Laboratory. And before we get started, I guess by way of further introduction, I'm going to describe a little bit about the research that I'm involved in with a few different teams, and that's mesoscale modeling, which I'm sure that you, within the series of lectures have gotten a feel for a variety of aspects of this. But one of the things we're primarily interested in at Los Alamos related to mesoscale modeling is being able to bridge between what we can learn on the right side of the screen from atomistic simulations over smaller length scales and shorter time scales, and use mesoscale modeling as a bridge up to the macro scale, where we have very practical questions that we need to be able to use models and simulation to answer. For example, this image in the upper left is showing the simulation results from a fragment penetrating into an explosive, and we could imagine that that if you zoom in close enough, you would see that features such as pore collapse at the atomistic scale present localized shearing deformations and localized heating that can contribute through the mesoscale type of simulations to the overall response that's important even in the macro scale. And so we view this in between scale as where microstructure is important is a bridge between those two. So that's an area of research that I primarily focus on, including developing constituent continuum mechanics material models for the individual constituents, like single crystals and grain boundaries, for example. So the bottom line of this screen is that we can get this meaningful insight from the mesoscale simulations, but only if we get the theoretical details for the ingredients of the microstructure correct. And so that's what my research focuses on. And now the next slide, I'm just going to sort of reinforce our interest in applying these kinds of tools to shock physics applications. And so in this case, we have an explosive at the center of the screen that's being detonated. Well, not the center, I'm sorry, the lower left corner, but it's the center of this quarter symmetry cylinder. The explosive gets detonated, and that sends a shock wave, which pushes a thick copper-walled cylinder, and it's then plastically deforming. And because of the role of the microstructure, we see heterogeneity in this calculation that emerges, and that leads to the formation of localized flow and necking, which ultimately is significant in terms of defining the fragmentation pattern. So that was, kind of a quick introduction of my research interests, as well as connecting that with the topic of the lecture today, which is the, trying to make a connection between the lectures that you've already seen and the ones that are yet to come, and what the active deformation processes are in the wake, so to speak, of a shock wave. So I'm going to summarize then the objectives that I'm hoping to make with this set of slides. The first objective is to reinforce what's already been learned and discussed in previous lectures from Lauren Benedict and Bill Anderson on shock waves. So that maybe will be a bit of a rehash of what they've already described and discussed, but I hope that I'm pointing out or alluding to more about the connection with the structure of the shock waves. Then the second point is something that I think you'll see a lot more of in the lectures in the following weeks, which is that this shock wave structure is often experimentally characterized by free surface velocity. That just happens to be a diagnostic that's been readily available for many years, and so it's common. So I think that you will learn more or see more about that in the upcoming lectures in the following weeks. But one of the main distinct points I want to make in these lectures is that you can think of the shock front itself, rather than thinking of it as a singularity, a discrete jump between two states. You can think of that as a transient material deformation process from one state to another. And the deformation rate that's imposed in that process leads to a competitive process between different deformation mechanisms. And then the other state variables that are involved in this process, like the temperature, the shock pressure, and the evolution of dislocations, they kind of help sort out this competition in defining what the dominant mechanisms will be. So, and then I also, will summarize some of the common deformation mechanisms that I believe have already been discussed at length by some of the other lecturers, including Amit and Irene. And I think last week was Michael Demkowitz's talk on photon drag. So all of those combined to set up, let's say, a menu of mechanisms that are available to the material in accommodating an imposed deformation. And I'm just going to briefly recall them. We won't dive into as much theoretical detail. But then to make the point, the final point is that the kinetics of these mechanisms affect what the ultimate wave structure looks like. And so that's the objectives of the lecture. So I hope I understood the instructions correctly. I hope that this is close enough to what was asked from me.
Yes, that's good.
So, thank you. So we're going to represent shockwave behavior by this model that I've got on the screen in the top of the slide, which is not the only way to impose a shock into a material, of course, but it gives us a convenient model to frame the discussion. So we have a rigid piston that's pushing on some material, and the material is confined in a rigid cylinder wall. And so the importance of that rigid cylindrical wall around the material is that it imposes a constraint on the deformation mode. So for an isotropic material, we'll everywhere see a uniaxial deformation mode if it's a homogeneous material being compressed. And then the rigid piston, its role is to ensure a specified particle velocity, and I'm sure that you've heard these terms already in the course of the lectures, along the interface between the piston and the compressed material. And so as this compression unfolds, what will happen at a sufficiently high velocity is we're going to see the wave which separates the undeformed region from the compressed region, and that wave is going to travel from the left to the right, in this case, at a predefined, or not at a predefined, at a velocity that characterizes that shock wave. So that's the wave speed, capital U, subscript S. So I use capital U's in these slides to indicate the wave speed. And the wave speed, of course, is different from the particle speed or the particle velocity. So you can think of the particle velocity as the velocity at which the actual particles appear to be moving to an external observer. So if we're standing here watching, we see all of these particles in the dark gray region. They're going to be moving at a velocity lowercase u, subscript p for particle. So that's the particle velocity, all of the material points in this dark region. But the boundary between the two regions is moving at a faster velocity, and that's the wave speed, capital U. So this is just a rehash from Lauren and Bill's lectures. And then you'll recall that there are some equations, analytical expressions, that represent conservation of mass, momentum, and energy for this system, and are generally applicable to the one-dimensional shock waves. So that's a relationship between the state in the undeformed region, labeled subscript 0 here, and the compressed or post-shock region, labeled 1. Switch to laser pointer. Yeah, I'm happy to do that if somebody can tell me where I would find that. Let's see. Is anybody
menu?
Menu? Which menu? Let's see. I see something called more. I see annotate. Is that what we want? No. Pointer. On this same screen. I don't know which screen. I don't see the option to change it to a laser pointer. Right click. Oh, let's try that. I don't see anything under right clicking. Maybe it's because I'm sorry, I don't see a menu option for changing my pointer to be that laser, to make it bigger.
Yeah, that's, someone says
So
click on the pen. If you see a pen symbol on the bottom left.
A pen symbol on the bottom left. No, I don't.
I don't see it on mine, so I don't know. Well, if you don't see it, just keep going on. Use the cursor. He says, never mind. So, okay. That's fine. Just go ahead. So you're mute, DJ.
Okay, is everything working now?
Yes.
Yes, okay. All right, so the one difference in these conservation equations from the previous lecture notes you'll see is that I write them in terms of the axial stress, sigma, which is different from the pressure because we have contributions of the axial deviatoric stress. And that's important when we're talking about deformation mechanisms that can accommodate or relieve the deviatoric stresses, like dislocation accommodated slip, for example. So that's the main difference from the equations I'm going to be showing and the ones you've seen previously. Okay, so but so why do waves have a structure that's affected by the mechanisms? That's the focus of the lecture. So recall that the Hugonio is the locus of viable shock states. And so if we plot Hugonio like in the lower left, you know, this fine blue line, that is the locus of attainable states from some initial starting point. And the locus itself doesn't define what the path is between states. So for example, if we wanted to go from 0 to 1, you know, we would not travel along this Hugonio locus to get between 0 and 1. The actual path is the Rayleigh line, which if the slides work correctly, yeah, then that's this red line that's connecting state 0 to 1. And the wave speed for the wave that is separating the material from state 0 to state 1 travels at a velocity that's related to the slope of this Rayleigh line. So Rayleigh line is just a straight line between the 2 points on a axial stress versus specific volume Hugonio. And the slope of that is this m given in the upper, or given in the equation shown in the slide. And that's related to the wave speed by this expression that's shown. So, and of course, the particle velocity is kinematically related to the wave speed via the conservation of mass. So that's this expression shown here, and I believe that you've already seen all of these equations in Bill Anderson's lecture notes. And so, you know, from just the slope of this Rayleigh line and knowing the initial specific volume and final specific volume on those 2 points on the Hugonio, we can describe what an idealized perfect waveform is going to look like in terms of the particle velocity drawn on the y-axis here and position drawn on the x-axis. So we have 0 particle velocity out in front of the wave, and then the wave itself is moving. So this jump from 0 particle velocity to the particle velocity we've computed to go from 0 to 1, that interface, that wave front, is moving at the velocity capital U subscript 0 to 1. Now, if we were to shock the material harder from the same initial state, instead of from 0 to 1, we might go, let's say, from 0 to 2, and in which case the key difference is the slope of the Rayleigh line and the end state on the Hugonio. And so now we've got both a faster moving wave speed and the particle velocity behind it is higher. And so is the associated stress state and the compression of the lattice. So that's you know, just a refresh from what you saw in Bill Anderson's slides. But so we're building up to trying to add some structure to this. And so we could consider having a solid material, and the transition from elastic behavior to some inelastic deformation mechanisms occurs at what we'll refer to as the Hugonio elastic limit, which is shown as this discontinuity at state 1 on that stress versus specific volume shock Hugonio. So if we were to impact the material such that the final state was on this segment between 0 and 1, then that's just an elastic wave. And then perhaps it's nonlinear elastic, but the way I've drawn it, that's just it's linear. So that would just be a elastic wave propagation problem. But if we go beyond 0 to 1, then in our end state is, let's say, at this point 2, then there's going to be 2 slopes to concern ourselves with. The first one is from 0 to 1, and then the second slope is from 1 to 2. And so if the slope from 0 to 1 is greater than from 1 to 2, and when I say 1 here, what I mean specifically is that point on the HEL where that discontinuity exists in the Hugonio. If that slope from 0 to 1 is greater than from 1 to 2, then there's going to be 2 waves. One is the elastic precursor that carries the jump from 0 to 1. So that's shown in the lower right of the screen as this lower part of the step function. That's the elastic precursor wave. It's traveling at a wave speed that's determined by the slope from 0 to 1. And then the final jump from 1 to the final Hugonio state 2, that the velocity of that portion of the wave is slower because the slope from 1 to 2 is lower than from 0 to 1. And so it lags behind, which means the further that this wave propagates through the material, the more separation there would be between the precursor wave and that final wave to the shocked Hugonio state. Sometimes people call that secondary wave the plastic wave. There can be all kinds of inelastic mechanisms, and in fact, there can be more than just 2 waves. So I think, being specific about what you mean is good enough, but I might be sloppy during the lecture and talk about an elastic precursor and a secondary shock, the final shock wave or the plastic wave. That's maybe imprecise terminology. So if instead we have, we move that point, there's our first step. If we move that point and let's say go from 0 to 3, all in one shot, and this 3 is up sufficiently high, then the slope is greater from 0 to 3 than it is from 0 to 1. And so then there's only a single wave that takes us from the undefined region, 0, into the final Hugonio state at point 3 on this diagram. And at that point, the shock, the final shock wave has overtaken, its speed has overtaken that of the elastic precursor. So we end up with this waveform shown in pink, which, we might refer to as a single overdriven shock. And that doesn't mean that there isn't some multiple deformation mechanisms happening in this jump from 0 to 3. It's just that waveform is been overdriven, so it's all compressed into one single jump. Okay, well, we could just add more complexity if we want to. And so the more complexity we add in the shock Hugonio, which you'll recall is a description in some sense of the constitutive makeup of the material. So, in some sense, we're describing, the specific details of the material behavior by this shock Hugonio. So now we've got an HEL. Below the HEL, that's the elastic behavior. Above it, we're having a transition where there's some inelastic mechanisms that have been triggered. And then we've added in a phase transformation in this space where from the state 2 to this small blue dot, there's a transformation from one polymorph to another of the solid, or it could also be a transformation into a liquid phase. So if we go through the same process, we could see how we might get 3 waves through this, which are described by the slopes from 0 to 1, 1 to 2, and then 2 to whatever our final point 3 is. And if we instead shock a little harder so that point 3 is higher up on that Hugonio, then our slope from 1 to 3 is larger than from 1 to this beginning of the transformation point. And so then we've taken that 3-wave structure and we've changed it into a 2-wave structure where we just have the elastic precursor in this case, and then the final jump to the final state on the Hugonio, state 3. Now, this is just an example. We could have, moved these points around on the Hugonio depending on what the material is, and it could be that we would overdrive the elastic precursor before we could have collapsed these curves into just one way. Like if we shock it all the way to a higher state 3. So now we're going from state 0 to 3, and it's just one single overdriven wave. So with the same material, it's possible to get very different wave structures, so to speak, depending on how hard we hit it and what mechanisms we've activated also. Okay, so there will be some upcoming lectures that talk a lot more about different experimental diagnostics, experimental platforms, experimental techniques, as well as the measurement and diagnostics. But I just want to introduce the free surface velocity, and then that can be generalized to like a windowed surface velocity. because that connects in with what we're going to be talking about and some of the actual examples that we'll show later. So the wave structure within the material as the wave goes through the specimen or through some component can be inferred using a laser or some other device, which this is the experimental aspects and diagnostics are not my area of expertise. But those can be used to measure the free surface velocity over some time interval. And an important aspect of that is that free surface velocity is when the waveforms reach the free surface, meaning that there's all of the exciting action that's happening to the material has happened as the wave goes through, or the waves go through the material, and then they have some cumulative effect in terms of the velocity that breaks out onto the free surface, and a laser can measure that motion. In this case, a free surface of our cylinder at the end of the the free surface of the specimen that's inside of our rigid cylinder after it's been compressed by the piston. So I'm just going to mention here, in order to make a connection, that the velocity of the free surface is approximately 2 times the particle velocity within the wave, within the wave itself. And so if we measure some velocity time history at a free surface, we can correlate that or relate that back to the actual particle velocity of the wave. So this diagram on the lower left corresponds along the x-axis from our model of the shock compression, of the material. And we're looking at a spatial profile of the particle velocity at a given instant in time, where we have an elastic precursor and then a secondary wave to go to the final Hugonio state. They're traveling, of course, at 2 different velocities, and associated with them is 2 separate particle velocities. And so as these waveforms make it to the free surface, they will register as some velocity time history that could be recorded at that free surface. That's shown in the bottom right, and it's idealized, and in order to keep things simple. So I'm not being especially accurate. I'm instead trying to be illustrative here. But the idea is that we have a velocity that would be, we would see some T1, we would call that the arrival time of the precursor wave in this case. And so that arrival time would be related to the length of the specimen and the elastic precursor velocity, assuming it's sufficiently steady across the specimen, which it may or may not be. And then the later on, the wave to go from the HEL state to the final Hugonio state will arrive. And I kind of left that as a potential problem to be solved for discussion on Thursday as to what this T2 would be in terms of the variables on the screen here, and what an idealized time of arrival would be. But so that I'm just showing how a wave structure within a specimen can manifest as a velocity measurement at some free surface. So we're taking something that's happening spatially, and it's moving, that spatial profile is moving along the specimen in time. Eventually it reaches some surface where we can measure a velocity, and then that's recorded as a time history. So we'll be looking at time histories referred to as velocimetry, and connecting that with some of the mechanisms. So I borrowed this figure on the slide from Mark Myers' textbook, which is very relevant for the summer school, which is the Dynamic Behavior of Materials. And I just wanted to make the point, which I'm pretty sure this is a hand-drawn example, to characterize the point which I'm wanting to make here, which is the actual velocity time histories are not simple step functions. There's real characteristics of the deformation process that affect the overall shape. And so several important aspects of the free surface velocity time history are indicated on the diagram. So, if you could accurately resolve that initial rise, that's going to be related to well, the time of arrival will be related to the longitudinal wave speed, which if you know the density accurately, then that's connected to the elastic modulus. Of course, the height that we've mentioned already is related to the Hugonio elastic limit, which is an indicator of the transition stress from elastic behavior to triggering some inelastic mechanism. And that's usually in polycrystalline or single crystal metals. That's usually, dislocation accommodated plastic flow, plastic deformation. So then, we can look at characteristics of that plateau to understand something about the process of processes of hardening and evolution of dislocation behavior. In this case, there's also a phase transformation, and so we sort of see 1, 2, and 3 different waves, but the step between them is not flat. There's a finite rise, and that's associated with characteristics of the material response. And then the final Hugonio state, which is drawn here, is nice and flat. It's not always flat, not necessarily flat. And then we're not going to talk about it today, but the unloading behavior can also be informative, or how you come back and relax. And I believe Justin Wilkerson will be lecturing on spall strength and damage later in the series of lectures. And so the path back down and potentially up is highly related to that behavior that he'll talk about. All right, so let's consider that the shock wave is a transient imposition of some deformation loading history, if you will, rather than an idealized perfect jump between states. And so what I mean is that because on that previous slide we showed that there's a finite time to go from one state to another, there's actually a deformation history that evolves rather than just some discontinuous jump. And that history is important if we want to consider the aspects of the mechanisms that are responsible for accommodating the deformation, like plasticity. So let's just label along our x-axis, it's some position x, we've got some infinitesimal region, element of material, and I drew a blue box around there, but that blue box is infinitesimally small. But I'm going to label it, and what we're primarily concerned about is the length, because of this one-dimensional shock state. We don't care about what's going on in the other directions right now. But this length of the infinitesimal region is delta x, and as the wave comes across, let's consider that it can evolve rather than just being a discrete jump. And so the evolution of the size of this element as it gets compressed is going to be expressed as lambda times delta x, where lambda is the stretch ratio, or related to a compression ratio. So the density in the compressed state is equal to the initial density divided by lambda. So by I, I'm guessing that the lambda we have drawn on the screen right now is like 3/4 or so, 2/3 to 3/4, right? So lambda under compression is a value less than 1. And then I'm just going to throw some approximations out here in order to illustrate the point and start to connect things. But if you actually want to do some calculations, I think you want to go beyond these approximations and look at the actual components of the deformation gradient. But to avoid going into the details of what a deformation gradient is, I just wrote out a strain component, epsilon 1,1, which is equal to lambda minus 1. So in this case, the axial strain, if I say that this stretch ratio is 0.75, then 0.75 minus 1 is a negative 0.25. So that's telling us it's been compressed, and that's like a 25% strain there. So equally important is the strain rate. So the rate that this is being compressed is related to the time rate of change of lambda dot. Well, from conservation of mass, we know lambda is related to the particle velocity and the wave speed for that particular wave. And so if we have a steady wave, we could write out, or if we assume a steady wave, which means it's traveling at a fixed velocity, capital U sub S, then we can write out this stretch ratio, or this compression, the strain measure, if you will, as a function of time. And we could record that as a function of time if we knew something about the particle velocity, and as well as the wave speed. And so then the strain rate, we take a time derivative, and then we would see that the strain rate is related to the derivative of the particle velocity in time normalized by the shock wave speed. And so what's important there is that we just related the strain rate that the material is experiencing as the wave comes through to the free surface velocity that we can measure if we assume that the free surface velocity connects back to the particle velocity. And that's because if the free surface velocity time history is related to, let's say, twice the particle velocity as the wave comes through the specimen, then the slope of the free surface velocity is related to the time derivative of the particle velocity, right? So we have a relationship between strain and strain rate and what we can measure. And and I've idealized that in order to illustrate the point. But we can make more accurate approximations and still get at these measures. So that's the point, is that we can infer strain and strain rate from the time history of the measured velocity. Oh, okay. So the time, yeah, so I'm just repeating that. Okay, so that's the point that's highlighted at the bottom. Okay, so if we're going to impose some strain and some strain rate, well then, we'll take a step back and just talk about decomposition of deformation to represent different potentially competing mechanisms. And we'll start with the real simple example, because I don't want to write out real complicated material models to make these points. So if we impose a given deformation or strain, we can accommodate that by a variety of mechanisms. And a very simple case is if we have an elastic perfectly plastic solid, so that we're elastically loading the material up this solid red slope on the stress strain curve, then we reach the yield stress. So then it's perfectly plastically deforming, and of course, if we've perfectly plastically deformed to a total strain of epsilon, then we could imagine virtually unloading along the dashed red line to some plastic strain along the x-axis, and then that leaves the difference between the two, the total strain where we're actually at, and this virtual unloading to the plastic strain value. The difference between the two is the elastic strain, and that elastic strain is related with the current state of stress. So the total strain is imposed by our loading, or in this case, or what we're trying to connect to, we're inferring that from some waveform. And then the plastic strain can accumulate in this elastic perfectly plastic model with no increase or addition in stress beyond the yield limit. The elastic strain is associated with the stress, and so we decompose that strain measure, as we just showed graphically, into an elastic and a plastic strain. And if we were to take the time derivative of that, then we can neatly decompose that into an elastic strain rate and a plastic strain rate. And of course, real materials are seldom elastic perfectly plastic, but they provide a pretty useful model, actually, in interpreting some observed behaviors. But the main point then is to talk about this decomposition, where if we can think about the competition between active mechanisms as if we add a different term on this decomposition of strain rate or of strain for each active mechanism, then the competition that we refer to is saying, which mechanism is going to accommodate the total imposed deformation. And we're going to, so we'll dive more in on that thought here in a minute, I think the next slide. Another important decomposition, though, is between volumetric and isochoric deformations. So volumetric mechanisms are very important for phase transformation and pore crushing. And if you don't have any inelastic mechanism to accommodate the volume change, then that all goes to the significant shock pressures that you can attain. And so that's why you can get very high shock pressures with this uniaxial strain state. It's because there's often not a mechanism to accommodate a lot of that volume change inelastically. So instead we have, it's not elastic, but it's lattice strain, volumetric lattice strain, which leads to very high pressures. On the other hand, we do have plenty of mechanisms usually available to accommodate the deviatoric deformation. For example, plastic slip and twinning. And so usually by comparison, the shear stresses are small when compared to the shock pressures that we see. And that's wise because, we can accommodate the shearing deformation with these alternate mechanisms. So, and then I'm just showing here that we can relate the deviatoric axial strain, epsilon prime 1,1, to this lambda value that we talked about, the compression ratio or the compressive stretch. All right. So to summarize some of the prevalent deformation mechanisms in crystalline solids, I've kind of decomposed all of them into what I'll refer to as thermoelastic mechanisms. So that's these top bullets, which I mentioned. If we change the volume of the lattice, then that can be accommodated via thermal expansion or by increasing the pressure. On the other hand, if we change the shape of the lattice by distorting it, then that's going to lead to some kind of a shear stress. So when we distort the lattice, that causes stress. If we impose a deformation and we cannot accommodate those imposed deformations by stress relieving mechanisms, then we're left with high stresses. And in fact, that's usually what happens in the wake of a shock wave in a transient manner. And so some of the inelastic mechanisms, of course, are crystallographic slip, which is accommodated by dislocation motion, phase transformations, twinning, and the nucleation and growth of cracks and voids. And then the diagram on the bottom of the screen is just to show sort of how the lattice, which defines the stress state, right, might view the combination of multiple waves coming through, where we go from an initial ambient state, then we have some transition from that ambient state through an elastic precursor to an elastically loaded state, and then subsequently we've plastically slipped the material, so we have some mess of plastically slipped material that has now an evolved dislocation field associated with it, and then perhaps sometime later, there's a transformation from this particular lattice structure to some other polymorph. So maybe it looks like we're going from a cubic to maybe a HCP type structure there or something like that. So that's what the image on the bottom is meant to represent. But again, these mechanisms take time to operate. If there is not sufficient time, then we might early on see a large stress excursion in the wake of the shock wave or associated with the shock wave, and then that stress can be relaxed through the operation of these mechanisms. So we're going to have to do pretty quick, I guess, overview or just going over dislocation-based plasticity again. I'm pretty sure this has been discussed already at length. And the main point I want to make is that if we increase mobile dislocations or decrease immobile dislocations, then we can accommodate an imposed deformation by plastic slip more easily. And that's observed through the Orawan relation, which is that our shearing strain rate, which is this, related to the angle of shear as an array of dislocations travels through the material and causes these increments in slip on different crystallographic planes. So we increase the shearing angle through the dislocation motion. Well, that's expressed by the Orawan relation, which says that the shearing strain rate is related to the density, which is a line length per unit volume of mobile dislocations, multiplied by the magnitude of unit slip, which is the Berger's vector magnitude. So drawn here on this figure, again borrowed from Mark Myers' book, the Berger's vector magnitude B. And the product of those terms with the dislocation velocity. So if we increase mobile dislocation density while holding the other variables fixed, then that means we increase the strain rate at a given dislocation velocity. What that means is if we add more mobile dislocations, we can accommodate more plastic deformation in a finite period of time. So increasing the fraction of mobile dislocations is advantageous for reducing or making a softer material, whereas increasing the immobile dislocation density, which is dislocations that are trapped and stuck, that's going to actually serve as a barrier to the mobile dislocations, which, without going into details of any specific dislocation velocity model, basically if we increase the immobile dislocation density, we decrease the velocity that the mobile dislocations can move at, and so we decrease the plastic strain rate that we can or the amount of plastic deformation we can accommodate in a given unit of time. So I hope that this slide is really just a summary of what you've already seen in the lectures, but that we're going to reinforce that with some molecular dynamic simulation results here, where these calculations were performed by G. Chen, a postdoc working with Saryu Fenson in MST here at Los Alamos. And so they're looking at simulations of the evolution of, in this case, it's copper during compression when you start with a certain number of dislocation loops. But the material is relatively pristine. Within this box, we can see the dislocation loops, but there's no real impediment. And if we can increase the dislocation density from this state, all we're doing is increasing the availability of mobile dislocations to accommodate the plastic flow, so that what we observe is that the imposed stress versus strain softens as you move from a lower mobile dislocation density to a higher mobile dislocation density. And then the plot on the right, I mean, the results on the right are showing that even when there's a tangled mess of dislocations, there's still a very large fraction of mobile dislocations within this simulation. But I'm just reinforcing this idea that if we increase the availability of mobile dislocations, we're going to make the material appear softer. So given where we're at in time, I think I want to skip some of the slides. I've got some slides here on practical applications of velocimetry to parameterize the kinetics of various inelastic mechanisms. I want to skip through that to get to reinforce the main point. So I'm not going to go into a lot of detail, but this is just showing an experimental configuration. I think you'll learn more about such configurations. In this case, it's a gas gun plate impact experiment setup. And we use those results to parameterize models. One of the things I do want to point out, though, is that so this is instead of a free surface velocity, it's the velocity of a window, an interface between a window and the specimen. But for the purposes of the lecture, you can think of that as characterizing the particle velocity within the wave. And so you can see that these forms are very different than the idealized ones we talked about. And one of the things you see is that we have an initial precursor rise and then a relaxation or a decay before we climb back up to from the second wave. And that relaxation is related to the rapid generation of mobile dislocation segments, which allows us to relax the state of stress in the material. So that connects back to that point I was just making on the previous slides with the MD results. I'm not going to talk about that more here, but I'm just kind of getting into, or a segue into, the evolution of elastic precursor. So there's a separation between the elastic wave and the secondary wave. And then if we take the thickness of the specimen, that's indicated by these curves, and we go from right to left, we're going from a thicker to a much thinner specimen, we see that we don't get much separation between the two waves. And of course, that's consistent with what we said. They've got two different velocities. So if you have a thicker specimen, then you have more opportunity for the precursor to get ahead out in front of the subsequent wave. But we also notice that the magnitude of the HEL is descending. So that's referred to often as precursor decay. And these results on tantalum from Zaretsky and Cannell, I would encourage you to take a look at that paper, especially in the context of the homework problems I'm going to suggest in a few minutes. They characterize that decay very, very nicely in terms of the stress at the HEL and how it is being affected by propagation distance of a wave through a specimen. And so what the point here, to connect this back to the main theme of the lecture, is that the structure of the wave is evolving as it propagates through the material. Okay, so we can apply relatively simple models to analyze a precursor decay from free surface velocities obtained by running these types of experiments at multiple thicknesses. So then the free surface velocity at for a given thickness is a proxy for what we would, for the spatial profile of the waveform at different distances it's propagated through an ideally infinitely thick material. Okay, but these expressions are going to be useful for the solution problems. So this goes back to analysis done by Taylor in '65, and the reference is provided down at the bottom of the screen, which says that the spatial derivative of the stress on the HEL is related to the plastic strain rate in the HEL as well as some of the elastic properties of the material. And then we can recall the Orawan relation that I've just described, where my psi variable is the dislocation density, and that's the mobile dislocation density, and the Berger's vector magnitude and the dislocation velocity. And then here we're just introducing a very simple dislocation velocity model in order to close these equations. So we have that the dislocation velocity is somehow related, or some fraction of the shear wave speed, C subscript S, of the material, and that fraction is defined by an exponential function of the applied shear stress tau, but in the numerator is this parameter, tau superscript star. So tau, the numerator is a parameter, the denominator is the stress state. So there's some other important relationships that are required in order to solve the equations, and so that you don't have to go digging through the literature or derive these on your own, which maybe you can from the previous lecture notes. The effective shear stress is approximately equal to this ratio of the shear wave speed to the longitudinal wave speed squared multiplied by the axial stress. And the relationship between the plastic strain rate and the shearing rate associated with the Orawan equation is just this 2/3 constant for our case of uniaxial deformation. And I've got some parameters on the right side of the screen that pertain to tantalum. So the homework problems are to use that model and the semi-analytical solution from the previous slide, and then look over a range of initial mobile dislocation densities from like 10 to the 6th per square centimeter to 10 to the 10th per square centimeter. And I would suggest, you vary those in like a log space, right? You want to see large variations to see the effect. And then varying this drag stress parameter from about 500 megapascal to 5 GPa, and I don't know, pick, a handful of numbers in there. And over those ranges in parameter space, plot the dislocation velocity versus the stress and pick some interesting values. That's what I mentioned. Then the second homework problem is, or related to this homework problem, is how would you relate the rate sensitivity to this plot? So what can you say about the rate sensitivity of plastic deformation in relation to a plot between dislocation velocity and applied stress over a range, in particular the variations in the mobile dislocation density? Then the third one is plot the axial stress at the Hugonio elastic limit versus the run distance of the precursor wave for a few different values of that dislocation density and tau value. So again, these guys up here, the tau star here is the parameter. That requires a numerical solver, I think. I mean, maybe you can work out an analytical solution. That's fine, however you want to come up with that. So then I've got a bonus problem, which is to connect all of that to a magnitude of free surface velocity corresponding to the HEL as a function of specimen thickness. So the 3 plus a bonus, and then I've got some notes here. Check the units for consistency, and also, you can check into the literature, and there's probably a lot more recent stuff where people have used these tools, but this particular path of analysis was developed in these papers I cited. And then email me if you're really stuck, because it's possible that I made a mistake. I haven't solved this problem yet, so it's possible. And then I think we're kind of getting towards the end of time. I'm not sure if that's the case, Amit. We need to wrap up.
You can go on. I mean, we have till 4:30, so you can go on.
Okay.
If you have more slides, feel free.
I will. I'll continue then for a bit, for a few minutes. I have another call to take here in 5 or 10 minutes. So, okay, so we've really focused on. Well, we talked kind of about some idealized relationships between Hugonios, which again is a locus of attainable shock states, and that can be measured for a particular material. We talked about relating that to wave structure that you might observe, and we connected that with a measurement, which is velocity time history. Then we kind of zeroed in more on saying, okay, well, there's different mechanisms that could compete, but we focused in particular on dislocation accommodated plastic flow. So I'm going to just very briefly make some connection with phase transformations. So many crystalline solids have different polymorphs that can be stable under different combinations of pressure and temperature. And so this plot on the upper right side of my screen is a temperature stress equilibrium phase diagram for tin, which shows that of different combinations of stress and temperature, you can have different polymorphs of tin that are stable. And then the different curves that are drawn are showing possible trajectories through this landscape, if you will. And those trajectories would represent the actual shock process that the material is going through, or whatever the actual deformation process is if it's not a shock. And so the point is that depending on where you start at and the actual trajectory you take, you can access different mechanisms. And then this is an equilibrium phase diagram, but a lot of times the deformation happens so fast that the actual rates of transformation are important. So that's usually described as kinetics. So we're talking about if you have slow kinetics, that might mean that relative to your loading rate, or the speed at which you move along one of these curves through phase space, you don't actually settle into an equilibrium phase, and instead the kinetics are delaying the transformation into that phase, which will certainly have an effect on the observed measurements. So on the bottom of the screen is some velocity time histories for the shock loading of this tin material, experimental and then calculations. The experiments come from this publication from Mabire, and where they were especially looking at a transformation from beta to gamma in tin. And then Carl Grafe in the theoretical division at Los Alamos has done some modeling of the beta to gamma transition. And so all of these curves here in black are using infinitely fast kinetics, which means that the equilibrium phase diagram holds. Whereas if you have if you allow a finite rate of the kinetics, you can modify those waveforms that we're seeing. So to connect it back with earlier in the lecture, we see a bit of an elastic precursor here, then a jump, and then depending on how hard we've hit the material, we're seeing an arrival of another wave that transitions into the gamma phase, from the beta phase into the gamma phase. And the shapes of those profiles are being affected by the assumption of the kinetics of that transformation. The main points, so this is showing or emphasizing some modeling work done by Frank Adesio, also in the theoretical division at Los Alamos, where he was looking at comparing model of phase transformation in pure titanium crystals under plate impact loading with experimental measurements. And the main point I wanted to make is that, so we see a clear elastic precursor and then the initiation of slip and twinning at the HEL. The evidence, or the evidence of the phase transformation is very subtle in this curve. And so, and then likewise in these other modeling curves, those are very subtle arrival of another wave associated with the transformation. And so, the point here that I'm making is sometimes these processes are very much important and they're activated, but the diagnostic, we're looking at very small wiggles in the diagnostic in order to infer that behavior. And that leads to another topic, well, that I'll get to after this slide. So on this slide, I'm just reintroducing twinning as a viable mechanism. So in competition with slip, this image on the left is representing that we're leaving a relatively, ordered lattice aside from some dislocations that have propagated and left steps to accommodate a slip along some, slip direction, slip band in a crystal region. We can impose or accommodate that same deformation by twinning the lattice, and which one wins depends upon an awful lot of other ingredients in this competition, because it's a competition between slip and twinning, and you could think of that as an energetic competition, and as well as kinetic, in that if the slip process is slow to occur, the twinning process may take over. And so, for example, under increased strain rates or lower temperatures where slip is suppressed or can't happen fast enough, you might observe that more of that deformation occurs as twinning. But one of the main points or takeaways here is that if you squint your eyes and look at the macroscopic effects, so those are accommodating an imposed shearing deformation. And so we have oftentimes a hard time distinguishing between slip and twinning when we're looking at shock structure through velocimetry. So it's hard to discern sometimes. So both of those reasons, there's interest in being able to use X-ray diffraction, which I won't be able to do justice here in one slide with just a minute or so of wrapping up my lecture. But we're very interested in being able to predict what a diffraction pattern would result from a certain, let's say X-ray diagnostic, so an X-ray beam being oriented with respect to a specimen at a certain time in the progression of a shock wave, how that might evolve and how we can quantify the comparison with an experiment. So on this big black region in the middle of the screen is a simulated diffraction pattern at different times as we shock compress the material through some deformation history. And then on the right is the same material, and those are experimental diffraction images. The static image is before a deformation process, and then the bottom image is under a shock after about 300 nanoseconds after impact, which is somewhere in between the trajectory I looked at. And if you probably noticed these don't really match up that well, and that's because they're actually not the exact same conditions. It's not like for like, but it's meant to illustrate the point that the diffraction pattern is related to the deformation of the lattice, and the lattice deformation is a result of the imposed deformation and whatever competing mechanisms were operative to accommodate inelastic deformation. So the net, what's left over is the elastic lattice deformation. So this is some way to kind of constrain or close those models. All right, to summarize, the objective of today was to reinforce some of the discussion that's already taken place about shock waves, especially point out this connection between shock wave structure and what can be measured in terms of free surface velocities. To think of the shock front not just as a discrete jump between two states, but as a deformation process, and then to recall and discuss some of the common deformation mechanisms, and importantly, to learn that the kinetics of these processes affect the overall wave structure. So that concludes my lecture. I recognize I went over a bit, but I appreciate that you let me do so, and that you guys, many of you, stuck it out till the end.
Thank you, DJ. That was great. Very informative. If the audience has questions, please go ahead and type it in the chat. Or if you prefer, you can just unmute yourself and ask the question. I think there is a question from Peng Zhang. Could you explain the decomposition of dislocation, mobile plus immobile?
Yes, I skipped over that quite a bit. But so, I passed back to the slide.
He wants to know how to physically understand the difference between the two kinds of dislocations, mobile and immobile, and how to determine immobile dislocation density in practice.
Well, so conceptually, or at the simplest level, a mobile dislocation is one that can move. So it has the ability to overcome lattice barriers like a Peero's barrier and move on along its way. Whereas an immobile dislocation or a segment of a dislocation has become trapped for some reason. And so there's a variety, I guess, of ways that you can envision dislocations getting tangled up. But one is sort of a frank dislocation that's, been pinned at some, so if you imagine dislocations on particular slip systems penetrating through a particular, another slip system, and then a dislocation line hits those two dislocations and gets pinned there and tangled, that would be a way to immobilize a dislocation. So the total dislocation density is conserved and represented by the combination of those two things. Of course, that's a highly over-idealized situation. The reality is you have a distribution of mobilities of dislocations from zero, which is trapped in some kind of debris, and able to travel at some sort of unencumbered velocity, and those, there's actually a distribution between those end states. So this really is, I guess, the concept of mobile and immobile dislocations is somewhat a modeling construct to explain the competition, but I think it's a lot more complicated in reality. But you could just imagine the local environment in this mess. Some dislocations will be able to move without being tangled, and other ones are stuck.
Thank you. There's one more question from Avinash Dongare. The decay of elastic precursor is related to evolution of dislocations as the wave travels through the metal. The presence of interfaces is likely to have dislocations distributed in the system. Is there a way to analytically predict the decay behavior of such systems, meaning systems that have a lot of interfaces?
I think so. Yeah, I think if you start from that kind of simplified analysis of Taylor, but instead replace, so they assume constant mobile dislocation density. If you replace that assumption with something associated with the nucleation of dislocations associated with that shock front, or some model that expresses how the dislocation, state, I guess, will evolve as the wave is moving through the material, then I think you could, connect everything. I haven't done that, but I think it's an interesting idea. So, and if you have a model for dislocation evolution, there's no reason why you can't add some approximations or relationships about how the interfaces play into that.
Okay, any other question at this point? So related to that, can ask a question that a lot of this is based on the assumption of planar interface at the surface where you make the impact. So if the surface is rough and has some structure, does that affect the kind of shock wave that's produced?
Yeah, it does in a couple of ways. So, you can add heterogeneity. You can add heterogeneity to the wave, and then if your wavefront is not planar, then you can end up with, you can end up with more local interactions. So potentially, you don't have a pure longitudinal wave. You could have some combination of shearing components and longitudinal components because of so it's sort of creating a localized wave dynamic. If those perturbations are significant enough, then that can lead to large instabilities, and I think that's the content of one of the upcoming lectures. I can't remember who's giving that, but I think there's some talk about instabilities in flow, and I imagine that would be related to like Richtmeier-Meshkov and Richtmeier-Taylor instabilities, or Rayleigh-Taylor. I'm sorry.
Okay, thank you. Is there any other question for today? I don't see any in the chat. So if not, then what we'll do is end the session for today. And then thank you very much, DJ. And the students can work on the homework problems. And then you'll be back on Thursday with the solutions to the problems and more discussion.
That's right. I'll send slides to maybe to you and Michael that have more of those equations.
Great.
Okay, thank you.
Thank you very much. Have a good week. See you back. Bye.